So we spoke last time about the uniform distribution. It's the most basic type of continuous random variable. Yes. And yes, so we realized that basically it's the analogy of selecting a random number in between a and b. So if the distribution of this random variable is over a to b, then you see the fact that the altitude is the same for all the thin boxes that you stuck underneath it indicates that that each point is equally likely to be selected. So now there is this there is paradox known as Bertrand's paradox. Okay, just an example of some things that can happen when you're not careful. So a chord is randomly drawn on a circle of radius r. What is the probability that this chord is shorter than the length of the side of an inscribed equilateral triangle? So what I mean by that is you can see that here is a circle and an equilateral triangle inscribed in it will be 1 where what? With what's going to be true about the angles. The angles are all going to be the same. If it's an equilateral triangle, then all the sides are the same, which means if we place it, which means that the division of the central angle, if you just take the center of mass of this triangle and draw radius to the corners of the equilateral triangle, the angle has to be everywhere the same. Good? Okay. The angle is everywhere the same, which is 2 pi over 3. So we may decide what is randomness supposed to mean in this particular case. So what's the probability that the chord is shorter than the side of an inscribed equilateral triangle? Well, shorter means what? Means that this line segment, we can imagine that it falls at an angle smaller than 2 pi over 3. So anywhere the chord is drawn, you can connect the edges of the chord by dotted lines and measure the angle. That angle is supposed to be smaller than 2 pi over 3. Are you with me, guys? Just to recap, you understand what we're trying to do? Just to show that there might be some paradoxical situations here. And that is if I randomly, and the question is, what do I mean by random here? If I randomly draw a chord, what's the probability that this chord will be shorter than the length of the side of an equilateral triangle? So first, I might describe an equilateral triangle in terms of the angles. Yes? Yep. So what I observe is this, right? So if I were to draw an equilateral triangle, I can connect the corners of that equilateral triangle to its center, right? By those blue lines. And because it's an equilateral triangle, the angles everywhere are the same. And they divide 2 pi into 3. So the angle is 2 pi over 3. Good? So one way to evaluate randomness and to say that the chord is smaller than the length of a side of an equilateral triangle is to say that the angle theta is smaller than 2 pi over 3, where the angle theta can be anywhere between 0, it's a tangent line, and 2 pi, where it's the diameter. You understand? Anywhere the chord is drawn, I can measure that angle. Do you understand? So I presented it so that it fell, so to speak, parallel to the x-axis. But anywhere it falls, I can connect the points at which the chord is touching to the center, and there will be an angle theta obtained. And that angle theta will be uniformly, I'm presuming if it's going to be uniformly distributed between 0 means it's a tangent line, and pi. So what's the probability of 2 pi over 3? The probability will be then 2/3 that we get it. We get it equal to 2 pi over 3 all the way to 0. You understand? Because 2 pi over 3 to 0, the length out of pi is 2 over 3. Please confirm if you understood my explanation. And if not, please ask questions, guys. Okay, good. So the one value I evaluated here is that this probability, if I assume the angle is uniformly selected or randomly selected between 0 and 2 pi, sorry, between 0 and pi, the probability of producing a chord shorter than the equilateral side of the equilateral triangle is 2 out of 3. Good? That's what I just said. Now, there is another possibility, right? So what you can imagine is that when I draw the chord, it's equally likely to be any of the y values. So anywhere between 0 and r for the y values. Good? And if it falls, so to speak, on the side, you can imagine rotating it afterwards it fell to measure the distance from the origin, right? The distance of the origin, you can imagine rotating it so that it is parallel to the x-axis. Good, so that it's always, it can be assumed it always falls between y equal to 0 and y equal to r. In that case, if that has a uniformly distributed position, then the probability is that the probability smaller is the probability that y is bigger than this point. And what's this point? This point, it's cosine of pi over 3. It's 1/2. You see, cosine of pi over 3 times r, so it's 1/2 of r. So this length here is equal to this length over here. Are you following me, guys? Here it is in that calculation. The probability that y is bigger than r over 2 is going to be the probability that we draw a chord that is shorter than the side of an equilateral triangle inscribed in the circle. So it's y bigger than r over 2, which means its length is r minus r over 2 divided by r, or simply 1/2. Do you understand what just happened? So I got two probabilities. One of them is 2 over 3 and the other one is 1/2. Right? Is this strange, or you understand very well why that is happening? Yes, happy end of the weekend to you too. What is it? Clueless Monday, right? So depending on what you assume to be the random distribution, you see, if you do you understand the resolution to this paradox, right? When I say that the chord is randomly drawn, or you imagine dropping a line randomly on the circle, you have to decide what happens randomly. Is it that the angle is random, or is that the position, the distance, so to speak, of the chord center from the origin of the circle randomly distributed, was distributed randomly? If the angle is distributed randomly, then it's 2/3 likely that you will produce a chord that is smaller than the side of an equilateral triangle. And if the distance is uniformly distributed, then it is 1/2 likely. They're not the same probabilities. All right, so any reactions? No. Let X be a uniformly distributed random variable over AB. What is the expected value of X and what's the variance? As we learned, we can calculate the expected value by taking the integral from A to B of X times 1 over B minus A. And when I take that expected value, I obtain B plus A over 2. You see, just the integral here is X squared over 2, evaluated at B minus its evaluation at A. Here it is. And when I simplify, it's B plus A over 2. In other words, the average is going to be the middle between A and B, exactly the midpoint between A and B, which I think we have predicted. We could have imagined that, right? If I equally likely to get numbers smaller than the middle as I'm to get numbers bigger than the middle, then the average will be the middle. Good. What is the variance? Well, for the variance, I need to calculate the expected value of X squared and subtract from it the expected value of X and square it. The expected value of X squared, just what you do is you integrate X squared times 1 over B minus A. That happens to be B cubed minus A cubed over 3 divided by B minus A. And when you factor the difference of cubes, what remains is B squared plus AB plus A squared divided by 3. Okay, guys, do you follow what I'm saying? Since I do not see most of your faces and do not see reactions, I have no idea if I miss you entirely or you understand everything. So Naomi follows me. What about the rest of you? Okay, good. So it's just calculations here. Now I subtract the expected value squared, and therefore what I'm subtracting is B plus A squared over 4. Here it is in expanded form. Upon simplifying, I get B minus A squared divided by 12. So the variance is the length of the interval squared divided by 12. So the universality of the uniform random variable. So you might ask yourself, what other continuous random variables are there? So we have the uniform random variable, and this might be partially answering Shotaro's question. Yes, what are the continuous random variables? So clearly, when it's constant, it's continuous. You agree, Shotaro?
Yes.
Yes, right. If it's constant, it's continuous. So how would we obtain such a distribution? Very simply, you observe that when you divide the interval into many sectors, right, each sector appears equally many times. You see, so there is no preference to any of the sectors over the interval over which you calculate this random variable. And so what you have is you have those histograms that are all of the same height. And as you make the intervals shorter, you still observe the same observation. And so you conclude that you're dealing with uniform distribution. And what could there be other types of continuous random variables, and how could they be related to the continuous? That's the following theorem is going to answer this question. Okay. So this is the idea. So if I take x, and x is a continuous random variable with a probability density function x. You understand? So that by hypothesis, if you were to find a continuous random variable, it will have a probability density function. That is the skyline of your thin skyscrapers, of your thin rectangles. Make sense what that distribution is, right? So it could be very high, it could be not very high. The area under this skyline has to equal to 1, right? So it has a cumulative, it has a probability density function little f, and cumulative distribution or cumulative distribution function f capital F sub x. So what we can do is we can use that to create a uniform random variable. All right, we can say just x equal to the inverse of u, where u is a uniform random variable over 0, 1. On the other hand, we can generate. In other words, I can take u and I can simulate x. You understand? If you give me the uniform distribution, I can produce that density function out of the uniform. I can morph it to be that new distribution. Okay. On the other hand, I can do the reverse. I can use that random variable to generate uniform distribution. You understand? So if I have one continuous random variable, I have them all. If I'm able to simulate one continuous random variable, I will be able to simulate every other continuous random variable, at least in theory. Okay? So at least in theory, if I know the uniform distribution, then I know all the distributions. Okay? And here is how that is supposed to work. So observe that, first of all, that the cumulative distribution function, it's a function from R to 0, 1. Yes, from R to 0, 1. It's an increasing function, and it hence will be invertible. Definitely when we don't have logs, when it's constant, right? So that would be an increasing function, and it will therefore be invertible. Okay, so so what you can do is you can let u be the uniform random variable over 0, 1 and calculate what's the distribution inverse, right? You see, maybe distribution inverse will map 0, 1 onto R. This interval would be made real. It is defined, and what you can set y equal to f inverse of u, and then the question is, what's the probability that y is less than a? That's the cumulative distribution of y at a, and its derivative, it's simply the derivative of this probability. You agree? Which, because the function is increasing, I just apply fx to both sides, is the derivative of u less than equal to fa. And what is that? That's the derivative, fundamental theorem of calculus here. You see, it's the derivative of this integral from 0 to here du, because this u is uniform, so its density function is 1. Good. So when I take the derivative, what am I getting? I'm getting little fx. So y and x have the same probability density functions. They are identically distributed. Good. On the other hand, I can try seeing if I can use that random variable x to generate the uniform distribution. So what I do is I'm going to actually calculate the. I'm gonna create a function which is the cumulative distribution of x. Good. And I'm going to see what that would be. So if u is this function, so the probability that u is less than or equal to a is simply the same as the cumulative distribution of u at a. And when I take its derivative, I will get the density function of u, which I hope to show equals 1. So the derivative of this function is simply that, that fx is less than or equal to a, which is the same as x less than or equal to the inverse function less than or equal to a. And when you take the derivative of that expression, what do you get? The derivative of that expression is the derivative of, look at it, x less than this value, it's just, this is just the cumulative distribution of x evaluated at this number. So it's the derivative of the cumulative distribution evaluated at its inverse, which they cancel each other out. So that's the derivative of simply a, which is equal to 1. Okay, of course, guys, you have to observe one small thing. So this is only true if the cumulative distribution is strictly increasing. Otherwise, it's not invertible, right? So here it is assumed that the random variable is defined over an interval and it's non-zero over that interval. Okay, so that will make the cumulative distribution increasing, and rather than simply at some points just constant, because where it's constant, that's where it's not invertible. Right? That can also, so in other words, that the proof that I'm showing you here is not good proof when the random variable has spaces where it's identically equal to 0. Although you can modify that proof to work in those cases. This is showing universality in the case where the random variable is defined over its support not to equal 0. Good. All right, and that concludes this portion. Now we talk about normal distributions, which is one of the very important distributions there. Okay, so normal distribution, guys. So if a continuous random variable z is, it's said to have a standard normal distribution if it has this form, right? If the function is phi z 1 over root 2 pi e to the minus z squared over 2, and it's defined for z between minus infinity and infinity. Good. So how do we observe that this is indeed a proper distribution? Well, you need to first, that's why we divide by this factor, is that observe that the integral from minus infinity to infinity of e to the minus z squared over 2 dz, it happens to equal to root of 2 pi. And observe this as follows. Okay, so here I'm introducing some ideas from Calc 3. So I hope you remember it enough to understand it. So first, the integral from minus infinity to infinity of this function, let it be some I. Now, clearly I can change the variable z into x and into y. Those are dummy variables that will not change a thing. Do you agree? So I can calculate what is I squared. If this is I squared, it's this number multiplied by itself, where I can write it one time with x, with a dummy variable x, and one time with the dummy variable y. Good. When I multiply those integrals, I get the double integral minus infinity to infinity, minus infinity to infinity, e to the minus x squared plus y squared over 2 dx dy. Okay. If for some reason you don't remember your Calc 3, again, I have a quick review of that on my website, or if you're very interested, I can just do it after class, right? I can, but I hope most of you will, like, what is most of you? Like 10 people maybe hopefully understand how this integration is working. Do you? Mm-hmm. So what does it mean, guys, right? If you want to review again after class, I can show you quickly why that works. So this integral is what? This integral means that I am finding the volume underneath this curve over the entire real number line. And it's much more convenient to do that using polar coordinates, right? So the polar coordinates, and I can explain if you want to very simply why you make the substitution. It ends up being the same as expanding a giant circle. So the giant circle is drawn from 0 to 2 pi. That means going around. And the radius goes from 0 to infinity. You have e to the minus r squared over 2. And the reason you have this r factor, I can explain very simply, okay? If you don't remember how to change variables in polar coordinates, I can try to help you there. Okay, which when you separate this integral, it becomes integral of 0 to 2 pi d theta times the integral 0 to infinity r e minus r squared over 2 dr. Good. Now this is simply 2 pi, and this is a simple U substitution, ending up equal to 1, ending up being equal to 1. And so I squared ends up being equal to 2 pi, and I to root of 2 pi. Now I went over that very fast, and if you don't remember Calc 3, you might be confused by several instances here, right? Or if you have never taken Calc 3 somehow. So I can explain that after class if you desire. But how many of you understood the explanation? So Shutaro, Naomi, okay, interpret maybe. Only 3 people. What about the rest of you? All right. Again, guys, stay after class. So for instance, I mentioned something about your exams, if in case you're just joining. I almost finished grading them. Naturally, I observed the group work or other ways that people receive the answers. Perhaps the answers are not theirs. That is some things that I observed. But regardless, most of your scores for exam 1, so don't be so terrified or devastated, were not good. So there were many mistakes that you made, right? So and among good students as well. So what we will do is we will see how you do on the second exam. Are you working on it, by the way? How is it going with the second exam? Not too difficult, less difficult than the first exam, more difficult? Pretty hard? Well, but so guys, so don't think with your faces always going to be well. I see it's hard. Now you agree it's hard. If you will need help with that second exam, I will try to assist you after class or other times we have available. Okay. And we can discuss once I post your solutions. Once I post your grades for exam 1. We can discuss the questions one by one, right? And your raw score I will record. Possibly I will post a different score, right? Well, I just want to see what you do for exam 2, how well you do that, how much do you study on your own rather than just group work, and then decide what should be the grade. But it's not the grade of the exam, because for some of you, for many of you, it was in the 60s. For some in the 70s, only 1 or 2 90, and you might say a questionable 90, like a 90 that makes me think somebody else received it. Okay, anyhow, back to this topic here. So Phi of Z is the integral from -infinity to Z of this function, right? So that's basically just the cumulative distribution. It's just the integral from -infinity to Z of the density function. So there are several important symmetry properties. So you can see that the density function, here it is, it's even, right? It's an even density function. So that will tell us quite a lot about its probability. So we know that the density function at -z is the same as the density function at z. So it's an even function. And there is symmetry of tails because the density is symmetric. That means that phi of -z, it's 1 minus phi of z. The curve looks like a bell. I'm hoping you have seen this curve, so let me show you. It's the familiar bell curve. And it looks like this, right? Here it's that bell curve, and this is the table for the cumulative distribution. Good. So you can see that area of the tails is the same if I select Phi of Z or Phi, so basically because of that, I see that if I want to calculate the area at minus Z, I might as well calculate calculate 1 minus the area all the way to Z, right? So for example, to calculate the region of this white tail, I might say take not of this white tail, let's just say this. Suppose that I wanted to calculate, here is my graph, and I wanted to calculate this. Okay, this is my minus Z. So instead of calculating this area, I can use the symmetry and say that this area is the same as this area. Agreed? This area is the same as this area here. Okay, for Z. Now, what is this area? This area, it's the cumulative distribution at Z. That would have given you this area. And so what all you have to do is you take 1 minus it. One minus it will be 1, remove this orange region. Good? Good. So this can be seen by just looking at the graph, or you can do it formally. Notice in my graph, I assume that minus Z is the negative number, right? Which is in fact, when you use those tables, that's what you assume. But here it's the calculation for any Z, positive, negative, right? The probability that Z is smaller than or equal to minus Z is the same by symmetry, or probability where Z is bigger than little z, yes? Which is 1 minus the probability that Z is smaller than Z, which is just like what we imagine, right? So formally, it's just this. You make the right substitution, the right U substitution, and you get this formula. So there is also symmetry of Z and minus Z. They have they are both. If Z has a standard normal distribution, then so does minus Z. Okay. So the reason for that is what's the probability that minus Z is less than or equal to Z? It's the probability that Z is bigger than or equal to minus Z, which is 1 minus the cumulative distribution of Z at minus Z, which by definition, well, by what we calculated before, is equal to the cumulative distribution at Z. Okay, so here let's calculate the expected value. What's the expected value of the normal distribution? What do you think, without any complications? What is that?
From minus 3 to
Sorry?
From minus 3 to 3 in the Z.
No, what's the expected value? I'm asking now. All right, so Z is distributed from minus infinity to infinity, but from minus 3 to 3, you're thinking about most of the probability is gathered from minus 3 to 3, like 97 point something percent, I think, or more. 99, I think, percent. I don't remember the number, but yeah.
Would the expected value be where the bell curve is the highest?
Well, not necessarily, but in this case, maybe. Not necessarily, right? The expected value is the average, right? So the bell curve, you see the function is symmetric. Look at it. The density function is symmetric about what value? Yes, Naomi, exactly, right? So the reason for that is seen easily. Look at that. It's the integral from minus infinity to infinity, 1 over root 2 pi z e to the minus z squared over 2. Now, that must be immediately equal to 0. How do I know that? Well, I see that because z multiplied by this value is an odd function, right? So it has positive region to the right of 0 and negative to the left of 0. So they cancel each other out. They're identical, right? You have the if you look at z times e to the minus z squared over 2, if you were to draw the curve at 0, it's 0, right? And then it's basically it's twisted through the origin, right? So whatever on the right you see positive, you see the corresponding area to the left, but with a negative sign. So it cancels each other to 0. Make sense? Now, what's the expected value of z squared? Well, that we need to use integration by parts. If you took Calc 2, right? So it's reverse product rule. So that is the integral from minus infinity to infinity, z squared e to the minus z squared over 2 dz. It ends up being equal to, well, you see, first of all, I'm going to use the symmetry that this is even. So I can say it's double the integral from 0 to infinity z squared times e to the minus z squared over 2. Good? And next, for this integral, I'm going to use integration by parts, it's called, or reverse product rule. So how do I reverse product rule here is that I just take those functions and I do not bother them, right? So it's remember, guys, how to do integration by parts, do you? So it's this, right? So this function is the function that we will, well, not quite this. I'm breaking it. I'm breaking the function into z times z e to the minus z squared over 2. Yes? Now, because what is in parentheses is essentially a chain rule. What? It's good. It's a good chain rule. So I'm going to integrate this function. This is the function that I called g prime, and this is the function that I call f. F is the function that so first I will have to have f g. So f is what I don't touch, and g prime I want to know what's the antiderivative of g prime. The antiderivative of g prime is e to the minus z squared over 2, right? With a minus, because when it comes down, it would cancel the minus. So that's where you see. So what you see here is f times g, which is that the minus is from here, z multiplied by e to the minus z squared over 2. Good. So I'm explaining like this way because, well, actually, I suppose that either you know integration by parts or you do not. Most of you are supposed to know it, correct? Right? If you haven't, if you're just sitting in and somehow you don't remember integration by parts, I'm happy to review it after class or to explain it from scratch. The idea is very simple. Good. So then, and here I add just the integral of g now, right? So this is f prime g. So f prime, the derivative of z is 1. So I'm just integrating this. Now the integral of this I already evaluated before. This is from 0 to infinity. It's just 1/2 of the 1/2 of root 2 pi. Remember, we calculated the integral from minus infinity to infinity. It's root 2 pi, and this is just half of it. So the answer is 2 over root pi multiplied by root 2 pi over 2, and the result is 1. The expected value of z squared is 1. Now, what is the variance? The variance is the expected value of z squared minus the expected value of z squared. but the expected value of z squared is 0. So the variance is equal to 1. Okay? So the standard normal distribution has variance equal to 1 and standard deviation equal to 0. Good? So if z is a normal distribution and we can label x to equal mu plus sigma z, it is said to have the normal distribution with mean mu and variance sigma squared. Yeah? So let's see what's the expected value. The expected value of x is just the expected value of mu plus sigma expected value of z, and the expected value of z is 0. So the answer is that the expected value is mu, which is natural, right? I just scaled this this z by sigma and shifted by mu, so the average should have shifted to this mu. Now, what is the variance? Variance is the expected value of x minus mu squared. Now, x minus mu is just sigma z, so that's the sigma z squared. So that means I can factor out a sigma squared. So it's sigma squared times the expected value of z squared, which is 1. So it's sigma squared, okay? So the variance of this x is sigma squared, and the expected value of it is mu. Good? So the other thing we can do is if x is normally distributed with mean mu and variance sigma squared, then we can convert x into the standard normal variable. Okay, so that means that if I were to, what I can do is I can take x minus mu divide by sigma, and I will get my z. Let's see what sort of distribution do we get, what sort of density function. So for this x, the probability that x is less than little x is the probability that mu plus sigma z is less than or equal to x, which when solving for z, it's just the probability that z is smaller than x minus mu over sigma, which is this cumulative distribution at x minus mu over sigma. When I take its derivative, what do I get? I get I get the function phi of x minus mu over sigma multiplied by the derivative of the inside, which is 1 over sigma. And so I get this is the distribution. This is the density function. 1 over root 2 pi sigma e to the minus x minus mu squared over 2 sigma squared. Good? And this, I think, Valeria, what you meant when you said 3 standard deviations. So you have the 68, 95, 99.7% rule, right? And that is if x has mean mu and variance sigma squared, then the 68% of the area under the curve is between minus sigma and sigma. 95 is between minus 2 sigma and 2 sigma. You understand what that means? That's just very simply, if this is my distribution, this is mu, and let's say that within 1 standard deviation, so this is minus sigma, that would be the 68%. Next would be somewhere over here is minus 2 sigma, 2 sigma, that would be 95%. And then if you move a little bit further, if you move a little bit to here, so about 99.7% of the area will be within 3 standard deviations from the center. Good? So here is a simple example, okay? So let x be normal with mean -1 and variance equal to 4. What is absolute value of, what is the probability that x is smaller than 3 exactly in terms of the density function? And what is it approximately, okay? The cumulative distribution function, you might kind of say this way, okay? So this is the cumulative distribution. All right, let's do it together. Maybe it's a bit hard to type. So here's what we do. So x is between -3 and 3. Now the mean is equal to -1, so I'm adding +1 to everything. And variance is 4, and I want to divide by the standard deviation, root of variance. So I write x plus 1 over 2, it's between -3 plus 1 over 2 and 3 plus 1 over 2. So that z is between -1 and 2. Now the probability that z is between -1 and 2, using the fundamental theorem of calculus, it's the cumulative distribution at 2 minus the cumulative distribution at -1. Do you agree? Now the cumulative distribution at -1, it's the same as 1 minus the cumulative distribution at 1. Good? And so when I simplify it, what do I get? I get, it's the same as the cumulative distribution at 1 plus the cumulative distribution at 2 minus 1. And the approximation using the 68, 95, and 97 thing rule, right, is as follows. So the probability between -1, that z is between -1 and 1, plus the probability z is between 1 and 2, it's equal to the probability that z is smaller in absolute value, smaller than 1, plus the probability that z is smaller than 2 minus the probability z is smaller than 1 divided by 2. Do you agree? Can you see that? So that would be 0.68% plus 0.95 minus 0.68 divided by 2, or 0.815. You understand how I carried this calculation using that 68, 95, 97.7 rule, 99.7 rule, I'm sorry. Yeah. So guys, if you are confused by something, you let me know before I move on, right? It's a boring section, and yeah, if I can explain something better, you let me know. So now let's talk just briefly as an example about the folded normal. Let y be equal to the absolute value of z, where z is the standard normal. Find the mean, variance, and the distribution of y. Can you do that without my help? Can you do that in 4 minutes? All right, so let's do it together, I suppose, then. So here is the integral of, so let y equal to this absolute value of z guy. Now, expected value of y is the integral from minus infinity to infinity of absolute value of z. And because this graph is, because this function is even, I might as well just say 2 times the integral from 0 to infinity of z times 1 over root 2 pi e to the minus z squared over 2 dz, which is a simple application of reverse chain rule. Yes, simple application of reverse chain rule, which you see the derivative of z squared over 2 is just z, right? So it's just the same thing as 2 divided by root 2 pi of minus e to the minus z squared over z evaluated from 0 to infinity, and this number is simply equal to, when I apply 0 and infinity, it will simply equal to 1. Right, so it's 2 divided by root 2 over pi. When I simplify it, it's 2 divided by root 2, it's root 2 divided by root pi, or root of 2 over pi. You understand how I obtain the expected value? The expected value is simply root 2 over pi. Good? Now, what would be the variance? The variance is very obvious. Basically, since the expected value of y squared is the expected value of z squared, right, is equal to 1. That means that variance of y is the expected value of y squared minus the expected value of y squared, and that's equal to 1 minus 2 over pi. Just square this number, right? If I square y squared, that will be the same expected value as if I just if I take the square of z. Okay, and to calculate the density function, that's not too difficult. I simply calculate here. So the probability that absolute value of z is less than or equal to y, it's the same as z between minus y and y, which is the cumulative distribution of the normal at y minus the cumulative distribution of the normal at minus y, which can be simply written as 2 times the cumulative distribution at y minus 1. And when I take the derivative, the derivative will be 2 times the normal distribution, which you might have guessed, because this distribution is just, when you take absolute value, it's like it's folded onto itself. So you have 2 copies of the right portion of it. Okay. So guys, you understand? I go through that rather fast. I hope you follow me, and I'm a bit kind of operating on automata with minimal thought on my part. I'm hoping you're able to understand me then. Could you confirm? So here are a few things that I will skip it. This is just if x is a normal random variable and we have those parameters to calculate this probability. That's the end of this lecture, but I want to move on. So I want to talk a little bit about central limit theorem. Okay. So why are normal random variables so frequently used? And that's because of the central limit theorem, and that states the following. Okay, if I have a sequence of identically distributed independent random variables, each having mean mu and variance sigma squared, then if n is very large, the distribution of the sum x1 all the way to xn is approximately normal, with mean n multiplied by mu and variance n multiplied by sigma squared. So the distribution of the sum of those variables is going to be approximately normal. Okay, So that's really that's a major theorem that makes this distribution, the normal distribution, very frequently useful. So clearly, of course, the expected value of the sum is n times mu because it's the sum of the expected values. By independence, the variance will be n multiplied by sigma squared. Okay, so then when we want to calculate, we're not going to prove this theorem. We don't have the tools to prove it here, and we will not develop them in this course, right? I need other ideas here, but that theorem you can just take it to be true for granted, right? So when you calculate x1 plus all the way to xn less than b, that amounts to the probability that, well, that I can just, if this is approximately normal, I might as well subtract the expected value and divide by the standard deviation, because that makes this random variable approximately standard normal. So this is approximately having variance equal to 1 and standard standard deviation. Sorry, variance equal to 1 and mean equal to 0. Let me just release my cat. Did you hear how he was screaming? Yes. So what we see is this is basically what you in essence do. So you see to calculate that the sum is less than b is very similar to just calculating to plugging into the cumulative distribution of the standard normal the value b minus n times mu divided by square root of n times sigma. That's a very useful result. So here is an example of how that might work. Are you ready, guys? So I'm not explaining why the central theorem is true, but I'm just showing you that if you accept it to be true, then those are the consequences. So insurance company has 25,000 automobile policyholders. If yearly claim of a policyholder is a random variable with mean 320 and standard deviation 540, approximate the probability that the total yearly claim exceeds 8.3 million. You understand how that is supposed to work? So imagine that that for this insurance policy, I mean, it imagines that the people are essentially the same, right? So like you have many copies of the same people. So how much they claim in damages each year is on average, you just look at all the claims and you average, it ends up being 320. Yeah, $320. And then you calculate the standard deviation just for this for all the policyholders, and you find that it is 540. So what might be the probability that the total amount that the insurance company has to pay up is more than 8.3 million? That's the question. So here is how we solve this question. You see, so what is the total claim? Total claims is T. It's equal to x1 plus x2 all the way to the 25,000 customers, right? So you add up all the customers, okay? And we're interested in the probability that T is bigger than 8.3 times 10 to the 6, or 8.3 million. Good? Now, what do we know about the expected value of T? The expected value of T is the number of clients multiplied by the mean. You agree? Because it's the sum of the expected value. So it's 25,000 times 320. What is this? And then we divide by the standard deviation. Yes. So the standard deviation, and the standard deviation multiplied by the square root of n. N is the number of people. So it's 540 square root of 25,000. Good. When you simplify this number, when you simplify this number on the side, you see that, why do we divide it? Because this is approximately a normally distributed random variable, standard normal, right? This is approximately standard normal. So what I do is to each side, right? To each side, I subtract expected value of t and divide by the standard deviation of t. And the result is approximately a normal random variable, a standard normal random variable. So when I simplify the right number, I get something like 3.51. So z is supposed to be bigger than 3.51. Good. Now it's an entirely outdated way of doing that, but you see that those values are calculated in the tables. Okay, so in the tables, at least if this were the table that you receive, you can look only positive z square. So here is 2 digits, and here is the third digit. You see, so what am I going to look here? So if I want to know what is z bigger than 3.51, I write 1 minus the cumulative distribution at 3.51. Now 3.51, I can look into the table. Here it is, right? So actually here I don't have the 3.5, right? It's beyond this number. I need more entrances, right? So here the best estimation that I can have based on this graph is I look at the closest value to 3.51, and that of course will be here, 0.990. That's the best I have here, at least by this graph, because here it should be going to 3.5. This is 3.0, 1, 2, 3, it should be going to 3.5. And then I look at the column. But since I don't have it, the best estimate I have is 0.990, which is what I place in here. So it's 1 minus 0.990, which is approximately 0.001. Actually, the number I obtain is too large. I will get a smaller number. You see, because here I should go to 3.51. You can naturally use a computer to estimate it, right? You have software. So for example, if I were to use my calculator, on my calculator, let's see, I can just select the distribution. So I select normal distribution, mu 0, sigma 1, and I can select 3.51. Three 0.51, and what I'll get is 0.00022, right? Not 0.001, but a much smaller value of 3 zeros after the decimal and followed by 22. You know, if you see, it's kind of like this. You have this on your calculator. You can install easily a software to do that much better than those graphs. So those graphs are of course outdated. But if it were an in-class exam, you would have gotten a piece of paper like this and you would have had to look through it, because calculators would not be allowed, right? So for exam purposes, of course, you know, I use that table over here to the best of my ability. Okay, so here is, it can be shown, a remark, it can be shown that the sum of two independent normally distributed random variables, x and y, with means mu x and mu y, and standard deviation sigma x and sigma y, is a normal random variable with mean mu equal to mu x plus mu y, and standard deviation, which is the square root of the sum of the variances. Here is another example, right, of how normal can be applied. So you drive in traffic and you wonder maybe about the situation. So the amount of weight in units of 1,000 pounds that a particular bridge can withstand is a normal random variable W with mean 400 and standard deviation 40. Okay, So W is normally distributed, let's say, with mean 400 and standard deviation 40. If the weight of a car is a random variable with mean 3 and standard deviation 0.3, how many cars would have to be on the bridge so that the probability of structural damage would exceed 10%? Okay, so how many the cars we just observe the cars, and we know that the average is going to be 3,000 pounds and standard deviation of 0.3 pounds, right? We don't know if they are normal or not. So here is how we are going to estimate the number of cars. So suppose that there are n cars on the bridge, right? The total weight of these cars is t equal to x1 plus all the way to xn, right? Where each of them is supposedly independent random variable. So when will damage occur? Damage occurs when total weight of the cars exceeds the capacity of the bridge to hold that weight, right? So imagine that the bridge, on some days it holds better weight, on other days it's not as good. So it's a random variable itself. So T must be bigger than W. You see, we know that W is a normally distributed based on the information we were given. Good. So what we can do is we can say T minus W. We want to know what's the probability that T is bigger than W. That is the same as the probability that T minus W is bigger than 0. And so what's the expected value of T minus W? The expected value of T minus W, it's the expected value of T, and T it's n cars, so it's each car weighs roughly 3,000 pounds. So it's 3 multiplied by the number of cars, minus the expected value of W, which is 400. So it's 3n minus 400. So far, so good? Now, what is the variance of T minus W? Well, because T and W are independent, we're assuming they're independent, right? So how much the bridge can withstand on a particular day might be independent of the number of cars. It depends on maybe the atmosphere or who knows what, right? And we presume it's independent. So variance of T, it's variance of T plus variance of W. Now, variance of T, it's n multiplied by variance of x1. And variance of x1 is 0.3 squared. Standard deviation is the square root of variance, right? So it's 0.3 squared times n. That's the variance of that's the variance of T. Now the variance W, it's apparently 40 squared, because we said the standard deviation is 40. So what do we do next? So when we simplify it, here's the number. So the probability that T minus W is bigger than 0, it's the same as the probability that T minus W minus its expected value divided by the square root of its the sum of, well, basically of the variance of T minus W. Right? I take the expected value of T minus W, divide by the square root of the variance. And that's supposed to be bigger than, well, I do the same thing to 0. I subtract expected value divided by the standard deviation. Yes? And that's approximately normal distribution of 400 minus 3n divided by root of, basically by the standard deviation, right? So this, I take therefore 1 minus the cumulative distribution of the standard normal at this number. So what do we want? We want now 1 minus this number to be bigger than or equal to 0.1. That's the condition, right? Understand? I want this probability to be bigger than 0.1. So then that's the same as saying that that the cumulative distribution must be less than 0.9. I just rearrange the sum, right? I take this 0.1, move it to the left, and move the cumulative distribution to the right, and I have this. So then I ask myself, for what value of Z will I get the probability less than 0.9? So I look at my table, and I look at where do I find 0.9. I look at those values, right? So 9, 3, 9, 2, 9, 2, 9, 9, 0. Right? I take the closest number to 0.9. So maybe I'll take the closest number you can take, or maybe 0.9015, or maybe 0.8997. You can decide which you prefer, right? So you can see you take some of those numbers, and then you look at the corresponding z-score. So what z-score do I have here? Looking at the table, the score we are looking for is z equal to 1.28. Naturally, I can use my calculator to do that a bit better. All right, let's see what it would say. Yeah. So one second. So I want 0.9 z to be bigger than that. So that is okay. So what you have is approximately it would be z equal to 1.28. Okay. So for z equal approximately 1.28, we have that the cumulative distribution is 90 or less. Yeah. So what you then have is that n has to be large enough to satisfy this equation, right? Is that z must be bigger than this fraction, and that happens when, if you just calculate and simplify, that happens approximately where the number of cars exceeds 117. Okay. So here is another example, maybe last example, and then we can call it a day, I guess. So a coin is tossed 1,000 times. How likely are we to get 550 or more outcomes where the coin landed on heads, given that the coin is fair? Okay. So we toss it for 1,000 times, and you get 550. If the coin is fair, what would that mean? Good. Think about it, guys. Can you estimate it? We tossed the coin 1,000 times and got 550. If the coin were fair, how likely that would have been? All right, let's try to do it together, I guess, so that you may go if you want to go. So let x be equal to the outcomes on first toss all the way to 1,000 toss. So the sum of those tosses apparently is going to be the number that we obtain, right? The random number we obtain. So what's the expected value? The expected value is that we get at each of them will produce heads is 1/2. So it's 1,000 times 1/2 or 500, yes? Each toss is independent of the next. So the variance, it's the same as 1,000 times the variance of individual toss. The variance of the individual toss is, it is the expected value of x1 squared, which still happens to be 1/2, minus the expected value squared of x. That is 1/4. So 1,000 times 1/4. Good. And what do we get? We get 250. Variance is 250. So the probability that x is bigger than or equal to 550 can be estimated as probability that x minus 500 over the square root, because if you see the distribution of x is approximately going to be normal. So it's x minus 500 over root of 250 exceeds 550 minus 500 over root of 2550. So it's the same as roughly probability that z is bigger than or equal to 500 over 5 root 10, which is approximately the probability that z is bigger than 3.16, which is 1 minus the probability that z is smaller than 3.16, which approximately is 1 minus 0.9992, or 8 out of 10,000. Right? If you do the experiment 10,000 times, you expect about 8 of those to produce 550 heads. So it's not very likely. Okay. And then we might ask ourselves, if the coin lands 550 times on heads, is the evidence enough to conclude that the coin isn't fair? What do you think? If you observe this thing, would you say the coin is fair or was fairly tossed? Remember, we estimated roughly as 8 over 10,000. You can increase it and say 10 over 10,000 or 1 in 1,000. So the likelihood of that is roughly 1 in 1,000. It could happen, but you know, right? So we can say well, you know what? So this is maybe a good thing for you to think about, and we will talk about it during the next class, right? Consider this evidence and ask yourself, what do you think that this is good evidence to suppose that the coin isn't fair, or maybe you have to be careful. All right, have a good one, guys. You can stay if you have questions. Yeah, I'm gonna go grade your exams, finish, I still have a few more left. And then once it's ready, should be before Wednesday, you should get your exams back. All right. Some of you did very well, but you know, not without extra help, I imagine. Take care.